Okay, calculus. The math at the beginning of this class is not that difficult. The first page is mostly explanations. In most classes you've done up to this point, your quantities have just been given as a number, a scalar. But sometimes you need both a scalar and a direction. So vectors have a tendency to have not just a length or magnitude, but also a direction. We do that by having a starting and an ending point. Its length we refer to as its magnitude, and it's written as like a double bar PQ. And what that means is you start at point P and you end at point Q. And all vectors of the same length and direction are equivalent regardless of where they start and end. The set of all directed line segments that are equivalent to a given directed line segment is a vector in the plane. In typeset material, vectors are usually denoted by lowercase boldface letters, U, V, and W. Written by hand, you kind of do an arrow. So to show two vectors are the same, if you can show that their distance and like the x and y direction are the same, that's good enough to show that they're equivalent. So we've got 3 minus 0 and 2 minus 0. Just the distance, 3, 2. We tend to write vectors like this. And then we've got 4 minus 1 and 4 minus 2, which is also 3, 2. These are equivalent because they come from the same, they make the same vector. It's not hard math, but really it's introducing an idea. Yeah. For any vectors, the most convenient form of the vector is the one with the starting position, the origin. This form is referred to as standard position because they're all equivalent. Usually we just refer to the one as the origin. So V is a vector on a plane whose initial point is the origin and whose terminal point is V1, V2. Then the component form of V is going to be just V1, V2. These coordinates are called the components of V, the x and y component. And then V is called the zero vector if it doesn't travel anywhere. Now, while many vectors are equivalent, they're only equal if for two vectors, v1, v2, and u1, u2, if v1 equals u1 and v2 equals u2. If v is v1, v2, we can assume that v is the vector from the origin to that point. So when you see a vector in this form, you assume it's from the origin. We will often refer to the length of the vector as the norm. So the magnitude, the length, the norm, all the same thing. If the norm of a vector is 1, it's a unit vector. So we tend to think of units in the real world as ones. You count by ones. If the lengths are ones, then it's a unit vector. And there's a unit vector in all directions, in the x direction and the y direction. So vector operations, you can add two vectors together and you just add their components. If you can multiply by a scalar, if you multiply a vector by a scalar, you just multiply each of the components by the scalar. Same thing with a negative, and same thing with subtraction. And here's a visual representation of what you can do, adding two vectors together by essentially putting one at the end, starting at the end point of the other one to get to the end. We're doubling or subtracting. So v is the vector negative 2, 5, and w is the vector 3, 4. Find the following. Half v is just half of negative 2 and half of 5, which is negative 1, 5 halves. So you just multiply each term by the number. W minus v is going to be 3 minus negative 2, 4 minus 5, which should be 5, negative 1, which will look something like this one. when you subtract them. So going forward one direction, back another. V plus 2W, well, I guess we can double W. And you don't have to write out all these steps. I trust that you guys can do this. It's V plus what's now 6, 8. So that would be negative 2, 5 plus 6, 8. Negative 2 plus 6 is 4. 5 plus 8 is 13. And what properties do vectors have otherwise? They're commutative, because addition is commutative. The associative property holds. Additive identity is adding the 0 vector. Additive inverse, if you add a vector and its opposite together, you get 0. And distributive property works as well. So a lot of the same properties that hold for a normal number system also hold for these vectors. Length of a scalar multiple. If you multiply a vector by a certain scalar, then you're multiplying the length by a certain scalar. Not hard to understand. Unit vector. If you want a vector of length 1 and it's currently a different length, you just need to multiply that each component of the vector by 1 divided by the length to get the unit vector in that direction. The triangle inequality applies to vectors. Obviously, the sum of the lengths of the two shorter legs of the triangle have to be greater than or equal to the sum of the length of the big triangle. Of course, they're equal if they're going in the exact same direction. Otherwise, it's less than. It's the same thing that works for triangles. You can't have the two short legs of the triangles touch each other and somehow add up to shorter than the length of the long triangle. Now, in 2 dimensions, for any direction, we have standard unit vectors. We refer to the unit vectors as I in the x direction, this bolded I, and j in the vertical direction. Since any vector can be broken down into its components, a vertical and a horizontal component, we sometimes can refer to vectors in this form, where v1i plus v2j. Doesn't really do anything for now, and I'll finish 11.1 in the next video.